Hi everyone. Christof, can you hear me okay?
Yes, I can hear you.
Great. Maybe we give 2 more minutes. I see a lot of people joining in the last seconds. So maybe we can start. So good morning everyone. So we are here for our third keynote in the joint LADC SPESC conference. And today with you, you have Christof Fetzer, who is a professor at the TU Dresden and is the head of the Systems Engineering Group. And recently, he has many works on integrity and confidentiality aspects for cloud computing. And these works have helped define a new research area that is being named confidential cloud native computing. But anyway, nevertheless, he is today not only for the papers in many conferences that we follow, such as DSN, Eurosys, Midware, Usenix Security, but also to the practicability aspects of this research in the industry, since Christof has founded several startups that help transfer the knowledge from academia to industry, but also to validate these results on more realistic and relevant environments. So, Christof, thank you again for accepting doing this keynote. It's a pleasure to introduce you and to follow this. I will now ask the organization to play the video and we come back as soon as the video ends. Okay?
Thank you for inviting me.
Welcome everybody. My name is Christof Fetzer, and in my presentation I will introduce an approach to ensure fail-stop execution in hostile environments. Most of you might already know about fail-stop execution, so that means that we execute a service or a program and we ensure that this is correctly executed. So whatever the program says, we faithfully follow the steps of the program. Or if we cannot guarantee the correct execution, we stop the execution before any wrong output happens. And we raise the bar a little in the sense that we consider hostile environments. That means environments where we have an adversary that has root access on the machine where we are running. So root access to the hypervisor, to the operating system, might be even an administrator of our application for which we want to ensure fail-stop execution. So we have some challenge here, and let's look into how we can solve that challenge. We are given a program that is written in an arbitrary programming language. It might use non-deterministic features like get time of day or having multiple threads that run in that process. That might use some mutexes to synchronize. So we are expecting there's some non-deterministic behavior with respect to the ordering of the outputs, and even the outputs might depend on the execution at hand, because it might depend on get time of day. And so what we want to make sure is that such a non-deterministic program is executed in a fail-stop manner. So either it produces an output that is computed in accordance to the program, or it stops execution before a wrong output is produced. So our program we could view as a non-deterministic state machine. And here on the slide we see on the right bottom some non-deterministic state machine. So it can get certain input, and it, in some cases, say it's in state S1. If it gets input 0, it might go to S2, state S2, or it might go to S3. So it has some non-deterministic behavior. And what we want to make sure is that even in such a state machine that is non-deterministic, we can ensure fail-stop behavior. This also implies that we cannot just use replication, because one way of ensuring fail-stop behavior is that we have 2 or more replicas, and we compare their outputs and ensure that a majority at least of them agrees. And in this case, if we have non-determinism, there might be a disagreement even if all the state machines are properly executed. We can formalize an execution as a sequence of transitions. So here on this slide on the top right, we see the state machine. And in one correct execution, we might take the path from S1 to S2, then S4, S5, and maybe then we have to stay in S5. So this would be one correct execution. And for the same input, we might also see a correct execution that consists of the transition from S1 to S3, then from S3 to S3, and so on. So we have 2 correct executions since for the same inputs, because we have a non-deterministic state machine. And so that means if we have 2 replicas, one might take the first correct execution and the other one, the one on the bottom. So there might be a disagreement on the states that they reach, as well as on the outputs that they produce, these replicas. Sometimes there might also be a disagreement because the execution is wrong. So say we have an execution in which there is a transition from state S3 to state S5, which is not permitted in our state machine. But if that happens in the execution, then this is, of course, an incorrect execution. And what we want to do in a fail-stop execution is to make sure that this transition cannot happen. So before that transition happens, or could happen due to fault or some external influence, we want to stop the execution of our program. Actually, in reality, we might even be happy with a weaker assumption in which we just stop the program execution before it produces a wrong output. So we might permit the program to transition from S3 to S5 as long as there is no output. Or we might even permit a wrong output in case we can ensure that the output that is produced can be detected as being wrong by whoever receives that output. But here in this slide deck, I will focus on the first one. So fail-stop execution, we stop the program execution before we have a wrong transition, actually, which means before we write a wrong content into the main memory. When enforcing fail-stop execution, we have to consider the failure model that we assume and also the threat model. So in the failure model, we chosen the following. We permit single bit flips during the execution by a CPU, so there can be 1 bit flip, and we trust ECC. So we have memory with ECC protection. We can assume that bit flips in the memory are detected by the ECC. And so we have some previous work that actually underlines our work from Eurosys 2016. An alternative approach would be, our failure model could be that we allow more bit flips. We even allow CPU design faults. We might also allow memory bit flips. And we can handle this more general failure model by using what we call encoded processing. And there's one instance of encoded processing that we have investigated, which is delta encoding. So we have for each variable, we have 2 encoded values that should show the same actual value, but they are encoded in 2 different ways, and we can detect if they are wrong execution by comparing these 2 values before we output the value. Anyhow, so the slides that I present today, they will be focusing on single bit flips, but we know how to handle more or tougher failure models. Before looking at the threat model, let us first look at the application context. So what kind of applications are we interested in? So first, safety critical applications, like in the automotive domain. Maybe we have some software components that run, say, in a car, and we outsource that. So we started in an edge cloud to ensure that we don't consume too much energy in the car. We run that on some external edge infrastructure. And if we have such edge infrastructure, this computing might have, or the computers might have, limited physical security. So here you see a picture of a shipping container where they are computing inside. So it's actually a rendering, but these shipping containers exist with real CPUs and also GPUs that sit somewhere in the open with very, very limited physical security. So adversaries could actually try to access these computers, try to manipulate them, try to steal some data. And there might also be limited security with respect to IT attacks. So therefore, what we want to make sure is that despite using a shared infrastructure with limited protection, that we can ensure the safety and the security of our critical applications. So we want to make sure that the data is protected, the code is protected, and the secrets that we use to encrypt data and code are actually protected. Our threat model assumes that our adversary has already complete control over the infrastructure. So the adversary might have root access to the operating system, the hypervisor, to even our application maybe, and might be able to change the voltage of the CPU via some machine registers. So, and the reason for this assumption is that maybe we trust some cloud provider of the edge cloud that should not be trusted. And so therefore, our objective is that we can protect the data, code, and secrets of our critical applications despite the adversary having already complete control of the infrastructure. And so what could such an adversary do to our code? Well, the adversary could change that code, replace it by his or her own code, could change the configuration of our application, could change the data that is read from disk or that is read via the network. The adversary might even be able to change the hardware, the motherboard on which the CPU runs, or can change the system software that is booted or is modified during the runtime, this system software. So there could be also multiple instances of our services and applications started. The adversary might change the voltage of the CPU to cause some incorrect executions. So therefore, we have lots of attacks that we have to consider and still ensure that the execution of our critical application is fail-stop. So the first thing that we have to make sure is that the right code is executed. So we have to make sure that the adversary doesn't exchange our safety critical code by some different code. So this is the first step. Ensure the code is not changed. And then we have to make sure that our code is executed in the right environment. say we want to execute that in an encrypted environment, and so-called enclave, which I introduce in a sec. So we have to make sure that the code is there, and maybe we also have to ensure that the enclave is executed in a context of a certain operating system. So we have to ensure right environment. We have to make sure that the code is correctly executed, despite, say, undervolting that might cause some bit flips. And we have to make sure that the state that we stored on disk, so the state at rest, is correct. It has not been modified or rolled back to an old state. And also, all the requests that we process should come from a correct client. Of course, if the adversary could control the clients and send us requests to modify the state of the service, this might be also a cause of invalid executions, which could cause human lives. So therefore, we have to address all these issues. And there's one more thing. So we have to also make sure that an adversary cannot just clone the service. Because if we keep state, say, on disk, and the adversary can clone 2 versions or 3 or n version of our code, then of course the adversary could selectively drop some of the requests by sending that via the network to a clone of the service. So therefore, we have quite some challenges there. And let me zoom into one of the challenges, just as a reminder that if we have an application, that typically the operating system, the hypervisor, does not trust the application. So it protects itself from the application. So it sandboxed this application. But on the opposite, application has to trust the operating system or the hypervisor, because if I do a system call in my application, the operating system accesses my memory in the application to, say, read something or to write something. The operating system needs access to the memory. So therefore, if I'm an adversary that controls the operating system, I can manipulate the memory of all the applications that run on top of that operating system. So that means in our threat model, where we assume that adversaries have root access that can change the operating system, in the traditional model, we lost, in the sense that the adversary has complete control over our application. Therefore, we need a different approach. So what we use here is confidential computing. So we can protect the application from accesses from the operating system, the hypervisor, any other software, as well as hardware. So you cannot access the application via DMA. So what we need, of course, is some support by the CPU. And I get to that point in a sec. So in a summary, confidential computing allows us that only the application code can access the memory of the application. And what we want to achieve is that all the data, code, and secrets that our application has at rest, in flight, and in use is protected from all the other software. And that allows us to actually outsource the management of the operating system, the virtual machines, the hypervisor, even the hardware, to an external entity that is not part of our trusted computing base. We actually can even outsource the application itself, so the management of the application. And what we use for that is a concept that is called an enclave. So an enclave is a kind of a memory region in which I, as an application owner, can put in some code, some data, some secrets. And this is an encrypted part of the memory where only the code that runs inside of that enclave can actually see the code, the data, and the secrets in clear text. Everybody on the outside, all the software, hardware on the outside, either cannot access that piece of memory, that range of memory, or if there is access, can only see encrypted memory. So in this way, we can protect our code, data, and secrets in use. Typically, data at rest is protected by the operating system. And this is not possible anymore because we don't trust the operating system to do exactly what we want to do as an application, because this might be managed by an external entity that we don't trust. So therefore, what we do is we encrypt data that we store on disk inside of such an enclave, and when we read it, we decrypt it and check that it's properly decrypted and fresh, that data. And we have been developing a platform that is called Scone, that was published in OSDI 2016, that actually supports that transparently. So your application is actually not aware that it runs in such an enclave and that the data on disk are encrypted. Moreover, we can also encrypt the data in flight. So by transparently encrypting all the network traffic in case the application doesn't use TLS. One important part of the confidential computing is that we can establish trust, because we have to start we have to put in some code inside of enclave, some data and some secrets. But actually, when we start an enclave, the adversary might see all that data and code that we put in there and might actually manipulate that code before the enclave starts. So therefore, we have to somehow establish trust in that enclaves. So therefore, we have to have some attestation. The attestation makes sure that the code that runs inside of that enclave is exactly the code that we want to run there. We can also ensure during attestation that the hardware is actually hardware that supports such enclaves, that it's up to date, has up-to-date firmware, has up-to-date hardware, and also that there are no open security advisory for that hardware that might affect the security of our application. Also, we have to make sure that all the clients that the application or service communicates with are also correctly started in a correct environment and the code was not changed. To do so, we need attestation. And so in a nutshell, attestation confirms that the initial state of an enclave, which is measured by the CPU and is a secure hash value of all the code and the data that is put in this enclave, is as expected. Also, during attestation, we can learn about some additional data item, typically a public key or a hash of a public key that the enclave during startup has created. So during startup, an enclave creates a random public-private key pair, and the public key is part of the attestation, which we call a report, which includes the Mr. Enclave, so the hash value of the initial state of the enclave plus a public key. This is signed by the CPU. And then what we do in the context of Scone, we have a configuration attestation service, which is called CAS, that checks that report, checks that this comes from is signed, the report is signed by an up-to-date CPU, genuine Intel CPU, and no security advisories. And then it checks in the policy certain other factors that need to be attested. And after that, it releases secrets to the enclave. And these secrets contain, for example, keys for the file system, arguments for that application, environment variables, files that are injected in the file system that might contain configuration files, and the configuration files might contain other keys and secrets. So in this way, we can configure the enclave with secrets and files and ensure that this initial configuration cannot be modified by an adversary. So far, we looked at making sure that the right code is executed in the right environment, so up-to-date trusted execution environment. We can actually also make sure that it's in a right operating system environment, so the operating system was booted properly. All the programs that were started in the operating system were properly checked. And now the next step is to make sure that an adversary cannot change the program execution by, say, undervolting the CPU to cause some wrong execution. So we have looked at that. So Artie, one of my PhD students, has looked at that with a system called Profi, which was published in SRDS this year. And this is based on some older work by a previous PhD student, which Dimitri, which was published in Eurosys 2016. And there we looked at a system that transforms programs using LLVM to add instruction level redundancy, or also transactions that recover after we detect a bit flip. And the idea of instruction level redundancy is as follows. All the operations are actually executed twice. So here you see add, where you add x plus y and assign it to z. And here we just add 2 times x and y. So we have 2 copies in two registers. So there's x and x2, a y and y2, and then the result is in z and z2, and we compare the results. And if they are not equal, then we go and crash the program. So we do a fail stop. And this is instruction level redundancy, ILR. And in the case of halved, we can add some tolerance and abort or execute the operations in a transaction, and abort if there is a miscomparison, and then we retry. And the process of building applications is as follows. We have to first transform the code, say it's C code, using a C-lang compiler or LLVM, and build the code to include the instruction level redundancy and optionally the transactions for recovery. Then we also need to use the scone cross compiler to ensure that we can run inside of enclaves, because inside of enclaves you cannot execute system calls. So you have to modify the way system calls are done, and one way to do that are cross compilers. We have also in scone now binary translation to do so, but since we anyhow use a cross compiler here, it makes sense to also use the scone cross compiler to combine the safety protection and security protection. And so then we combine these two and get a binary that is protected against bit flips, as well as having all the facilities to run inside of enclaves. Now the question is, how should we evaluate this system? In here we actually use an approach that was published in the literature, which is plundervault. So undervolting the CPU to cause real bit flips, not doing some artificial fault injection, but using undervolting to evaluate the system. And for that we have a simple program to test. So we have a multiplication of 2 values. We check if the result is the expected result, and then we continue in the while loop. Otherwise, we exit with an error code. And for the evaluation, we have timeouts. So we stop the loop after 35 seconds or 100 seconds, and then we iterate for 100 times or 1,000 times then. And what we see, if we iterate 100 times, in 100% of the cases, we exit with an error in native code. And if we have 1,000 iterations, we sometimes see some iterations where there are no bit flips detected, or the result was always correct. Then we run that in the enclave, and there we have slightly better values. So in case of 100 iterations, between 93 and 99%, of the tests where wrong results detected, but there were some tests, more tests where we didn't detect anything. Okay, so then Profi without recovery, so only instruction level redundancy, we actually see very little, nothing. That means without recovery. So 0% of the results were wrong. So by having instruction level redundancy, we actually can detect all the faults that we got through undervolting. If we do recovery, there we see that we have some wrong results. So recovery actually reduces the correctness a little. And therefore, if we really want to have fail-stop behavior, we don't want to have recovery Profi without recovery. So just instruction level redundancy seems to be the better approach. If we look at the overhead, there we can see that the recovery actually costs us in overhead. So we have here some benchmark programs, and there we see that just by running in the enclave, the overhead is not that high. By having transactions, we actually we get some more overhead, and if we have scone plus transactions, so Profi plus recovery, then we have even higher overhead. But if we have just scone plus ILR, so no recovery, then actually overhead gets a little lower. So these are benchmarks, so you see different performance there. If you look now at some more interactive application like a HTTP server, and there we see, and hopefully you see that in these smaller graphs, that if we have a HTTP server in C, there is no difference between the alternatives. So we get about 20,000 transactions a second, independent which variant we are running. If you have actually a Rust version, there you see the orange one is native execution, and then there is Profi and Scone only. They have the next best execution, and then if you have half so with recovery, then the performance goes further down. If you now look at instead of Rust, we look at Python, then actually the Scone variants are faster. So Scone and Profi. So we have slightly different execution using Scone when we have Python, and there in this example there we have better performance. But if you look at the throughput of Python versus the C, of course there is an order of magnitude difference there. So therefore it's not that unreasonable that we might have a little better performance sometimes. Okay. Now let's look at another problem, this cloning of clients and services. And what we have looked regarding cloning are trusted leases. So there we have a paper, one of my PhD students has a paper in SOX last year. And there the idea is that we require that the enclave has a trusted lease before it can continue running. So kind of it has to stop if the lease expires. And let me try to explain that problem. Say we have some consensus like Raft. There in Raft consensus we have epochs where we have a leader, and say we have 3 different replicas in this case. And each epoch we have one leader. And now if an adversary might clone our replicas, what could happen? So we might have here the 2 clones on the top and the bottom. We have clones of each replica. So there's replica 1 and replica 1 prime, 2 and 2 prime, and 3 and 3 prime. And say the adversary also does a network partition so that the blue replicas and the pinkish replicas cannot talk to each other. So that means we might have two different leaders in the same epoch, and that means that Raft would be able to decide different values in the different clones. And the first kind of replicas versus the clone replicas, they might decide different things. And so the idea to solve that cloning is that we have leases, so we have a trusted lease service, and at any point in time, only one of the two replicas, so replica 1 or replica 1 prime, can get the lease. So therefore, only one can survive. So as soon as a replica's lease expires, it has to crash. So in this way, one could use leases to solve that cloning problem. And we have done that with the help of these trusted leases. So in this case, when we have trusted leases, we can make sure that only one of them can get lease. And say in this case, we have replica 1 and 2 having a lease, and replica 3 prime has gotten the lease. And since we have a partitioned network, replica 1 and 2, they don't talk to replica 3, 1. And so in this case, the blue replicas actually can continue and take their decisions. But maybe an adversary learns about this and does the following. It first ensures that replica 1 and 2 get the lease. So in the blue replicas, they elect a leader and decide on something. So in Raft, you have a decision log. So say there's a proposal of deciding A, and these two replicas decide on A. And then in the next epoch, the adversary steers the network in such a way that replica 1 prime and 3 prime get their lease. Replica 1 will crash because its lease has expired, but replica 1 prime goes up and 3 prime goes up, and the adversary might have partitioned the network and the disk so that replica 1 comes up and sees, okay, I'm the leader in epoch 1, so there's a proposal B, so I decide on B. So that in this case, we would have in the two partitions, in the clone and the non-clone partition, we have two different decisions, A and B. So to solve this, we have to make sure that the state at rest is correct. So let's summarize that problem again. So we have here the blue and the pink replicas, and they should be in different states. So when replica 1 prime continues, it should see that replica 1 actually decided already on A. So the log has to be visible to replica 1 prime when it starts, when it gets the lease. So therefore, what we do in Scone is to make sure that the state that a service reads is integrity protected, confidentiality protected, and consistent. So it gets the latest state that was written on disk. So we have one could call that a rollback protection, this consistency requirement. So we rollback protect this persistent state. And in this way, when replica 1 prime starts up and it sees the old state, it cannot continue because attestation will fail. So in other words, we also solve the problem of protecting the state at rest using Scone, and rollback protection is actually enforced by Scone CAS, our configuration attestation service. So one last point that I want to address in this talk is how can we make sure that the client is correct. So what we actually support is a mutual TLS-based attestation. So we can make sure that our peers are actually satisfying their security policy. So all services are associated with a security policy that is maintained by the SCON CAS. And what we can make sure that if two services want to communicate with each other, that they can only do so if they both satisfy their security policy and that they got the right client and service certificates to be permitted to talk to each other. So we have actually something that we call a network shield, and that network shield requires certificates, and these certificates and private keys associated with the certificates can only be emitted to a service, here in this case service A and B, in case they satisfy the attestation policy. So a little bit more concretely, when a service starts up, it gets attested and it gets certificates. Here, like a client certificate together with a private key that is signed by a certain CA certificate, and we can guide or we can generate dynamically these certificates with the help of policies, and in this way we can make sure that services can only talk to each other when they have the right, satisfy their policy and are part of the same application. So the attestation is guided by policies. Here is a very simple one on the slide. So each service is described what kind of, how it's attested, like one can specify the Mr. Enclave, so the hash value of the initial state of the enclave. One can actually specify a few more things that are beyond this talk, and we can define certain secrets that should be emitted to that service after a successful attestation. Okay, so what are the next steps? We are currently ensuring that this lease service and the SCON CAS, there's also only a single instance. So if you seen or listened, I actually didn't explain how you can make sure that the SCON CAS and also the lease service, there's only a single instance, because you need that too. And you actually need also fault tolerance. So this is some ongoing work. We have also some real-life use case with which we want to evaluate this system. But of course, there are lots of open questions that you could focus on in case you're interested in this topic. So one example is, how does it compare with Byzantine fault tolerance? In Byzantine fault tolerance, we need to assume that there is a maximum number of faulty entities. Here in this context, all the computers might be having problems. They might all have adversary on them. So we might not need that F, but we have different assumptions there. Like that our attestation is correct, that we can trust it. Also, we might not only want to have load time attestation, but also runtime attestation. So how could we support that? How can we make sure that this is portable across multiple clouds and CPUs? How can we improve the ease of use? And how could we support different protection levels? So there are lots of open issues that would be interesting to address. If you have any questions, I would be very happy if you would ask them and we can discuss about them. Thank you very much.
Thank you again, Christof. And now we open to the questions. So I see George is already raising his hand. George, please take the mic.
Can you hear me? Yep. Thank you. First of all, thank you for the nice talk. A very interesting talk and quite a bunch of work that you made a compilation of lots of work in this talk. It's nice to see. But in the motivation part, you talk about safety critical applications, And those applications, I see that they need some kind of they need to comply with some kind of real-time constraints, like meeting deadlines. So in your model, it was not clear which kind of synchrony you are considering for the distributed model. So I'm quite curious to see your words on the time domain safety and security. For example, if you have to comply with meeting deadlines, and I guess that you have to assume some strong time synchrony in the system, and this might make the approach more complex or simpler. I don't know. I'd like to see your opinion on this.
Okay, so thank you for the question. So yes, hard real-time guarantees are often required in dependable systems. In particular, if you look into automotives right now, there you typically have something that is hard real-time. I would say in this context, I would not make or take the hard real-time deadlines into the edge cloud, because you cannot really protect say the wireless link to the edge cloud. So I would prefer or suggest that we take a different approach. So we assume that we can, or we timestamp all the requests that we send there and the replies that we get there, and we make sure that as long as we get sufficient responses from the edge cloud, then we can actually continue. And maybe I missed to introduce one concept in that slide deck, and that is typically that you have, say, redundant replications in dependable systems. So you have not only one copy, but you run two copies. And the idea is here that you have one copy running in the car, and you have two or more copies running in the edge cloud, and then you can go with the continue with the one in the car that is hard real time, and you verify that one with the ones in the edge cloud. And so in this way, you have a little less constraints on the hard real time guarantees, because you then can use the kind of the local computation to go into fail stop in case you don't get confirmation from the computation in the edge cloud. Does this make sense?
Yeah, thank you. I was referring to more to soft real time, because yes, hard real time you cannot guarantee this kind of environment. I agree with that, but I think that we should be able to produce some good answers in the good time. In this kind of, for example, a car in the traffic light can receive information. If it's too late, it's better not to process this information. And when we put a adversary in the system, things can be quite complicated. So I was referring to soft real time, not hard real time.
Okay, if you go to soft real time, so my favorite approach is actually to timestamp everything with these days with real timestamps. So during my earlier work, we had mostly kind of local hardware timestamps. I'm much more convinced these days that we put real timestamps on everything using GPS times, for example, and then we can actually make sure that information that is out of date can be easily detected. So you do a kind of drop everything that is too old, and that would actually confuse the system. And I think that would allow us to build really simple soft real-time systems. So where we, as long as the cloud is fast enough, we get useful information, but we are not confused if the data is out of date, because that could also be safety critical. And there, kind of in a nutshell, we put everything on real-time stamps. We make sure that our clocks are synchronized with GPS time. There are ways, so there are papers. I have also co-written some papers where we can make sure that we can trust the real-time stamps from external clock sources, and then we can actually solve that problem. It takes a little work, but I think that is a solvable problem to detect out-of-date info.
Thank you.
Welcome. Thank you.
So while others organize their questions, I have one here.
Sure.
It's a very introductory questions, but relate to other things that are being discussed in the conference. So zero trust is something that has been mentioned for quite some time, and now there is this concept of confidential computing. So what is the intersection and what is the difference between these two ideas, in your opinion?
Yes. Yeah. So zero trust has been around and is actually very popular these days in business applications. So where you verify that you run in a certain environment, and confidential computing, I would say, is an extension of that. So you don't have trust in any infrastructure first. You verify everything. So that means before you provision any keys, any secrets to an entity, you make sure that this is actually the right entity in the right environment. So you establish trust by measurement in confidential computing and by running the software in enclave, so in encrypted regions of your memory. So that makes sure that you do not attest something that might be changed a second later by the adversary. So this is kind of, in a nutshell, it would be an extension, because we also verify, we don't trust initially, and we actually do not trust the whole system. So in zero trust, sometimes there is kind of, at least in some implementation, it looks like they do a measured boot, they measure things, and then they are happy with the context. Here, we really assume that all the time that there are adversaries on the system, and we have to protect ourselves from this adversary in the system. So we always assume there is no trust in any of the components that are around us, and we have to isolate ourselves from these components using these enclaves and ensuring via verification before we communicate, or attestation I should say, before we communicate with anybody, we attest that communication partner to make sure that they are belonging to the same application, they run the code that they are supposed to do, that they run on up-to-date hardware and firmware. And that allows us to isolate ourselves from a very strong adversary with root access. And so therefore, nutshell, it's an extension, similar assumption, but kind of extending it of being even less trusty in or trusting in this environment that we are running in.
Got it. So I would guess if someone wants to do a layered approach, would have to combine these two. Or how do you see these problems that we see now and then, that you have a bug being published that require people to patch their systems urgently because of some firmware update?
Okay, so there I would say patching is a really good use case for confidential computing, because it forces you to have a cyber hygiene. So every time you start a service with confidential computing, you have to first get attested, and there you check that the firmware is up to date, the software is up to date, and this means that your software cannot run if your system is not up to date. And so therefore you have continuous patching, and maybe yes, so zero trust is kind of part of that confidential computing, or it would be one instance of confidential computing. When I understand you right, you say 2 layers. So I would see that this is kind of one implementation that has this philosophy of not establishing or not trusting a established machine. So you first have to verify that, and we do constant verification. And we also do additionally isolation of the workloads to make sure that some parts of the software that we cannot verify, or system software, or users that have that are malicious and have access of the system, that they cannot access our data or modify our data and code.
Got it. Thank you. For those that are starting to work on that, I would also be interested in asking about support and other producers, because you did mention hardware requirements and then mentioned Intel. So what's the current ecosystem right now regarding the hardware support?
So there are different CPU manufacturers that support confidential computing. We have been using Intel SGX for a while because it allows us to protect individual services. There is AMD SEV that was very buggy for a while. Now with the AMD SEV SNP, it actually got better. So, but the level of protection is a different one. So there you protect the virtual machine, so you have an encrypted virtual machine, while in the Intel SGX case, you have one process, one service that is protected. So that means with Intel SGX, I can isolate individual services. In AMD SEV SNP, I have to isolate operating systems. So of course, I could do that by having each service that I care about in the individual virtual machine. And then I have to make sure that nobody can log into that. So from my perspective, I would like to have something that is a combination. So having both virtual machines, and inside of the virtual machines, I have the enclaves. And the reason for that, I can make sure that my enclave, my service is protected, and then I use the encrypted virtual machine to ensure that the environment of that enclave is protected. There can be some users that can log into this to do some maintenance, but I can protect this environment of the enclave, that there are, say, no side channel attacks, by limiting what applications can run there. There, I forgot one more CPU manufacturer, that is ARM. So ARM has also announced the Realms CPU extension. So this is very similar to AMD SEV. So they have also virtual machines that are encrypted. Also, Intel will soon have something that is called TDX, which are also virtual machines that are encrypted. So from that perspective, the main CPU manufacturers have some confidential computing infrastructure. Also, OpenPower has some, which is also like virtual machines. The Intel SGX I also like because it maps really nicely to containers. So there you can protect containers, while it's more difficult to use this VM approach for protecting individual containers. Okay.
Thank you, Christof. And how about availability of this in the off the shelf, let's say, like that? So cloud providers and hardware support in stores.
So you can actually run that on Microsoft Azure. So you can also, so Microsoft Azure has Intel SGX support, has all the features that one needs to run actually the confidential computing. We have also some virtual machine there for Scone, so you can actually try that out. So we have, for this all Scone framework, you can download. There's a community version. You can run that there, or we have a playground on the Azure that you can use. And there are some more cloud providers that will soon also provide this, also in Europe, that then have some hardware for confidential computing. So there is lots of opportunity right now, and you can easily start. So if people want to start with some research, they can get from us. Yeah, community edition. We have all the papers online. We have also lots of demos online, program code. And as I mentioned, there are lots of open questions that people could look at that can be solved and that are interesting for PhD students.
Thank you, Christof. So we are reaching the end of our time. I will thank you again, and I will offer to gather the questions here that are on the Mattermost or the chat and send to you later, if that's possible.
Okay, thank you very much for the invitation. Thank you. Bye-bye.
Thank you. Thank you all. Have a nice day. Bye.